Okay, in this lecture, we will discuss about the virtual ground, the concept of the virtual ground, and also we'll discuss how this is different than a real ground. We'll also see can it be shorted with a real ground. Okay, so first of all, let's try to understand the basic concepts, the underlying concepts of what leads to a virtual ground. Suppose I have an op amp, okay, this is my op-amp, and we know that op-amp has basically the two input terminals. Okay, we call this as the inverting terminal and this as the non-inverting terminal. Let's call it the inverting terminal to be V1 and non-inverting to be the V2, and this is my output terminal. And of course the op-amp follow a very simple equation that V out is equal to AV times V2 minus V1. Okay, so basically the op-amp simply amplifies the difference of whatever the input that I'm providing between these two terminals. The difference is amplified by the AV times. So this is different than the conventional amplifier, because in a conventional amplifier we only have a single input and the single input is just multiplied, but here the difference is amplified. Okay, so this is the main difference. The other important aspect of the op amp, we know that it is the gain is very high. Okay, the gain is very high. This gain is on the order of 1000 is very less, or it can be 10 power 4 or even more 10 power 5. Okay, so yeah, so this is a very important characteristics of the op amp, that the gain is very high. The other important characteristics of the op amp is that the input impedance is very high. The input impedance is very high, in the sense that it is so high in the orders of maybe tens or hundreds of mega ohms that in our analysis generally we consider the input impedance to be infinite. That means hardly any current is flowing inside the op amp. Even though there may be current, but that will be very small, in the order of the nano or picoamperes. So in our analysis, or to make it simplified, okay, to simplify the analysis, we consider this current going inside the op amp to be zero or negligible. So if I try to now rearrange this equation, okay, so instead of writing V out equal to AV into V2 minus V1, if I write as V2 minus V1 is equal to V out by AV, so V2 minus V out, V2 minus V1 is V out by AV. Okay, now suppose example, if I want to get maybe a finite value of the V out, let's consider I want the V out to be maybe 1 volt. Okay, to start with, that means the difference V2 minus V1 should be 1 volt by AV, and let's consider AV maybe 10 power 4. So that means V2 minus V1 is equal to 1 volt by 10 power 4. So this is equal to 0.1 millivolt. Okay, so that means if I want to get a finite output, okay, of course the value will be finite, because we know that we have the supply for the op amp, and it can be like 10 volt or 10 volt to minus 10 volt or 15 volt to minus 15 volt, right? So and of course we want it to be finite. Okay, we don't want it to be infinite. Or even if we consider it maybe 10 volt, the V2 minus V1 becomes 1 volt. That means the difference between the V1 and V2 are very small. They are so small that we can approximate that V1 is almost equal to V2. That means the condition is that if these two are almost the same, that means we cannot apply any input directly to the op amp, because whatever that I am going to apply, they're almost the same, right? So as soon as the difference is significant, right? So suppose if I'm applying maybe 10 millivolt, okay, so 10 millivolt into 10 power 4, it becomes 100 volt, right? So and because of which what will happen, the output just gets stuck to either VDD or minus VSS, depending upon which is higher. Okay, so or it goes to the saturation state. That's why this op amp is never used in this open loop condition. That means we never apply even the input directly to this op amp. So then how do we control that, or how do we make sure that these two are very close, right? So if you are not able to apply input, then how are we going to use this op-amp as an amplifier? So the op-amp has to be used in a closed loop condition. That means I should use my output to control the difference between V1 and V2. Okay, so let's go to one of the configuration, then things will be more clear. Okay, so I'm having an op-amp here, and what I will do is I'm going to ground this V2. Okay, I'm going to ground this V2, and this V1 I'm going to connect a resistor, and this the other end of the resistor will be connected to the output node. Okay, and maybe let's connect one more resistor here. Okay, and let's apply my input signal here, V in. Okay, and let's call this resistance to be R1, this to be R2. Okay, so now as we know that V1 is equal to V2 almost if I want a finite value, so in this configuration this resistor ensures that these two voltages are almost the same if considering I am having a finite value of the Vout. Okay, so that means because this is at 0 volt, this happens to be very close to 0, or almost we can say constant to be 0 or 0.1 or something like that, few millivolts or microvolts sometimes if the gain of the op-amp is very high. Okay, so that means this voltage is very close to 0. This concept is called, because this is like a ground, but it's not a ground because there is no current that is flowing inside the op-amp because it's a very high impedance. So this concept is called as the virtual ground. So this concept is called as the virtual ground. So this is acting like a ground. Okay, so we'll discuss more in details again. So this is called as the virtual ground. So this point which is behaving like a ground, but it's not a ground, so this is a virtual ground. We'll see this one more in details, and we'll also see how this is different than a real ground. Okay, the other thing is how this is staying near 0. Let's try to understand intuitively. This feedback resistance is not allowing to this voltage V1 to deviate from 0, because if you see here the equation that my V out is, we know that it is AV into V2 minus V1, and now since the V2 is 0, so my V out is nothing but just V1 is there, so minus AV into V1. Okay, so now because the gain is so high, so even it's slightly increasing, so suppose it has increased to a positive value, increased, then this V out is going to increase largely in a negative side, right? And it will throw this resistance, it will try to pull it back, that okay, you should not deviate here from 0. So for example, if it goes from 0 to 1 millivolt, so we know that this goes to, if it's a 10 power 4, so it tries to go to minus 1 volt, and through this resistance it will try to pull it back. So because it's going positive, so it's going negative, so it's trying to pull it back to 0. Similarly, if suppose this is decreasing, right, instead of increasing, so similarly if instead of increasing it decreases by minus 1 millivolt from 0, so then this will increase by 1 volt, and it will try to pull it back and pull it back to 0. So because there is a a difference in the sign of the voltage. Okay, so when this is decreasing, this is increasing. When this is increasing, this is decreasing. So through this resistance, it tries to pull it back to 0. So basically the V out is not allowing this V1 voltage to deviate from the 0 volt, or being different from V2. So with this we can easily analyze the circuit, and we can try to find out the gain equation. Okay, so now because this is a ground, like it's acting like a ground, so the current through this resistance R1 will be given by I. R1 is equal to V in minus R. Okay, so this is the current flowing through it, or you can say that more precisely V in minus 0 if I apply a simple KVL or Ohm's law. Okay, so V in minus 0 volt, so this is IR. Okay, and there is no current flowing through this. Okay, the current flowing through this is 0, and if you see the current flowing through R2 IR2 is, this is same as this is IR1. This is equal to IR2. And we know that IR2, I can write it as 0 minus V out by R2. So 0 minus V out by R2. Okay. So this is R1. This is R1. So now just if I rearrange this one and this two expression, I will get V out by V in is equal to minus R2 by R1. So this is the gain of this configuration. Okay. And the concept of the virtual ground is used to find out this gain. Okay. So now we also have to understand that this virtual ground is just a concept. It's just a node in the whole circuit whose potential is 0. So then the question comes is, what if I make it equivalent, or if I try to short with the real ground, what happens? Okay. So if there are, like, suppose some other voltage or ground, and if I try to short it, will there be a current or not? Okay. So let's try to understand this concept and how this virtual ground is different than a real ground by considering an example. So this is another example where I'm shorting this V2, and again here also I'm having a resistance at the input side. Let's call it as R. Okay. And previously we had called it to be R1. Okay. And I'm having a resistance. Let's call it the value of this resistance to be 2R. And let's have one resistance here, which is R. And let's have one more resistance, 2R. Okay. So this is my V out. Okay. So now here, if you see here we are having, of course, this two grounds in the, there are two grounds. One is the real ground 0, and the another is the virtual ground. Okay. So we may be tempted telling that, okay, so let's connect these two nodes, okay, and make this resistance and this resistance parallel, because ultimately there will be no current flowing through this node because both of them are at 0 potential. Okay. So this is a slightly misleading concept, and we should never try to short the real ground with a virtual ground. Why? Because the real ground is, can, source infinite current. Okay, source infinite current. Whereas the virtual ground, we know that it cannot source infinite ground because there is no we know that this is a very high impedance, and there is no current going source or sourcing or sinking from this op amp, and the current that it provides is only the current coming from the V in, or V in by R is the current that is coming through this one. Okay, so that's the main difference. Okay, so let's try to first analyze this correctly by considering the KCL and KVL, which is the right method to do the analysis. And then let's see by connecting this one, what is the error and how can we solve this error. Okay, so let's first try to solve in a correct way. Okay, so the current flowing through this one, we know that this is, let's call it this to be IR1. The current flowing through this, let's call it to be IR2. Current flowing this to be IR3 and IR4. Okay, we know this IR1 as we had done in the previously. Okay, IR1 is equal to V in by R. Okay, this is the current flowing through this, and this is also equal to, we know that this is IR2. Okay, and now if I want to know the Vx, therefore this voltage Vx will be, from this the current is flowing like this, so it is basically 0 minus the IR drop, 0 minus IR2 by into R2. Okay, using simple KVL. Okay, so that means this voltage is, we know that this is minus V in by R into 2R. So implies my this voltage Vx is equal to minus 2 times V in. Okay, so this is my you know this is my voltage. Okay, so because I know this Vx, okay, so I can calculate IR3 now. So therefore my IR3 is equal to Vx by R, which is equal to, because we know that Vx, so this is minus 2 V in by R. Okay, so this is the current that is flowing, and of course we can see here that this current, although the direction we have assumed to be like this from Vx to ground, but it looks like it's negative. That means the ground, the current, the actual current that is going is from the ground to Vx, because this is indicated by the negative sign. Okay, and therefore this current IR4, we can apply a simple KCL at this node. So KCL at this node means IR4 will be equal to, basically we can, because this current is coming out and this is going this one, so it will be IR2 minus of IR3. Okay, by applying a simple KCL at this node. Okay, so that means this is IR2 is, we know that what is IR2? This is V in by R minus, and IR3 is minus of twice V in by R. Okay, so that means if I sum it up, it becomes minus 3 V in by R. Okay, so now because I know the IR4, so I can easily calculate my V out. Okay, so therefore my V out will be, so if I apply KVL from here to here, so it is like Vx minus IR4 into twice R. Okay, so because I already know the value of the R4, so, and we know the Vx. What is Vx? This is minus 2V in, and IR4 is, sorry, I made a mistake, so this is plus 3V in by 4. Okay, because this minus minus gets multiplied. Okay, so here what I have here is 3V in by R, okay, into 2R. Okay, so if the R gets cancelled here, so therefore my V out is minus 8 V in, or implies, in this case, V out by V in, the gain of the whole configuration is minus 8. So this is the final relation between the V out and V in, that V out is 8 times V in. Okay, so now let's try to revisit and let's try to see what was the mistake when we tried to short this to ground and why it was. Because if you see here, if I try to short this to ground, so we'll see the error and also how to rectify this error. Okay, so assuming that I can connect this two. Okay, so if I have connected it, okay, that means thinking that these two are the same potential, we have to see that this ground cannot source infinite current. It can source only, or source or sink, whatever this one. Okay, but we can see that this current I3 is missing. Okay, so if I just try to make these two parallel, okay, and try to make an equivalent resistance, that means actually I'm missing one current, which is this current that is flowing, right, minus of IR3 through this resistance that I am missing. Okay, so because of which, and there will be an error in the calculation if I miss this current. Okay, so that means if I want to make an equivalent something like this, I should do write the whole thing something like this. So I have the op amp here. Okay, so I have shorted these two, but then we have to consider that there is one ground which is shorted, one more ground, and this is giving a current which is equal to minus IR3. Okay, and then only we can make these two resistance parallel, which is, if this and this are parallel, this is we know that this is 2R into R by 2R plus R, so this is 2 by 3R. Okay, so I have a resistance which is 2 by 3R. Okay, and then I have this 2R. Okay, so the equivalent resistance here is this plus this. Okay, 2R plus 2 by 3R. Okay, P out. And whereas the current that I am flowing here is one current is this one, which is the IR1, and then I need to sum up this current which is coming from this. So this current is basically, so the total current that is flowing through this now is I should say that the current I, let's call it to be IX. Okay, IX will be it's nothing but the IR plus summation of minus IR3, and we know that from our previous calculation, IR, we know that this is P in by R plus, and IR3, of course IR3 is negative, so this is 2V in by R. Okay, 2V in by R. So IR3 is negative, so minus IR3, it happens to be positive, so this 2V in by R. So the total current A here in this case is 3V in by R. Okay, and that is flowing through this resistance and it is giving the V out. Therefore, my V out is minus this IX into the total resistance, which is 2 by 3R plus 2R. Okay, so and this happens to be minus 3V in by R into, so this happens to be 3, and then this is 8R. Okay, so this gets cancelled, 3 gets cancelled, and I'm going to get minus 8V in. Okay, so now this answer is same as the previous one, which is PR by V in equal to minus 8. Okay, so fine, so we can short it, but the thing is that we have to understand that the virtual ground cannot provide infinite current, okay, like the real ground. Okay, so that's how, if I don't consider, if I don't consider this part, okay, if I don't consider this part, it's going to give me a wrong result. If I just short it this one and make this an equivalent, then this is going to give me a wrong result. So if I'm trying to short, I should consider that part. So this makes the analysis complicated. So the lesson from this analysis is that never try to short a real ground with a virtual ground, because the real ground can provide infinite current or sink infinite current, whereas the virtual ground, although its potential is zero like a ground, but it can like the current provided by it is limited, which is dependent on this V in. So that's the main difference between the real ground and the virtual ground. So the virtual ground is nothing but it's just a concept, it's just a node in a circuit where the potential is 0 volt. But the main thing difference from the real ground is that it cannot provide infinite current or source infinite current. Thank you.